So today I'm going to be presenting a piece of joint work with many co-authors, all of them lovely. And what we were trying to do is we were trying to look at distributed key generation and see if we could come up with something which our main priority in this work really was to address complaints rounds, I would say, but we also tackle other issues in them. Hold on. Okay, so first what I'm going to do is I'm going to give an overview of our contributions. When I'm doing this, I'm probably going to include quite a lot of jargon, but once I've done my overview, and I'm then going to tone it down a little bit and sort of say what is a DKG and that kind of thing. So our main contribution is a new construction of a DKG. The DKG we present is publicly verifiable. So unlike these VSSs, which Lefteris was just describing, where you need to have it such that if you want to get your share after you've gone offline and you want to check that everything's been done well, you need to talk to other parties in the scheme to make sure they don't have any issues. As instead, you can just sort of look at a transcript and check for yourself that it's okay. We don't have any complaints rounds. We get some pretty good efficiency, and most of the efficiency comes from the fact that our scheme is aggregatable. So second contribution is a construction of, I'm saying fully structure preserving here. What I mean by that is that the secret key is a group element. This is a little bit of a misuse of terminology because we're not in the standard model, and usually these things would be. But either way, what it means is we have what is essentially a unique signature scheme or a signature scheme where we can have secrets which aren't field elements, they are group elements, which goes very nicely with Algorithmic encryption. When proving our scheme secure, we do so not under your standard definition of DKG being like perfectly secret, which would assume that you can generate a public key and be able to perfectly simulate everything with a simulator. We actually weaken this notion because we think that it is very difficult to achieve, at least without multiple rounds, in the setting where you have rushing adversaries, so adversaries that might play last. So what we're more concerned about is, can an adversary that play last cheat? Can they break the resulting scheme? So we weaken the notion to cover that setting rather than the notion of perfectly secret. And with our new definitions, we're then able to talk about some new proving techniques. When we're proving our scheme secure, we don't have any rewinding at all, which from a sort of theoretical perspective is really nice because it basically means we don't need to worry about concurrency. And using our new proving techniques, we are also able to show that previous DKG, which I would consider to be one of the state of the art, the Pedersen DKG, is applicable to both AlgoMal and BLS, but not digital. Okay, so I'm now going to try and stop the jargon. I'll probably still have some, but I'll try and keep it to a minimum. What is the distributed key generation algorithm? What we're basically trying to do is generate a public key. We want to do this using what I'm going to call a trusted setup. This is slightly different to the trusted setup which Lefteris was describing, where you have just one party that sort of generates a secret key and then shares it out to everyone. Instead, it's a more of a distributed trusted setup, such as the kind that you would get with zero knowledge snaps. So the idea of a distributed key generation protocol is to generate a public key such that nobody knows the secret key, but you can still carry out certain operations as long as you have a threshold, a majority of players. So this might apply to threshold encryption. What that would mean is that if you have a database, maybe you don't trust one person to decrypt the whole database because maybe it contains quite sensitive information. But equally, you don't want it to be the case that you need all N people to decrypt the database, because what if one of them, I don't know, leaves the company, goes offline, is otherwise uncontactable. But what you can do is you can sort of say, if at least T out of N people are present, then we can decrypt the database. Likewise, we have a similar idea with threshold signatures. These have become sort of, I'd say, more received more community attention since blockchains become a bigger thing, because you end up with situations where you genuinely do have these signatures which can release huge amounts of money. So maybe if you have quite a lot of money and you don't want to sort of trust yourself to store it, but equally you don't trust it on just one server who might be corrupt, you might share it out amongst lots of servers such that all of them need to collaborate in order to compute the signature in order to sign a transaction. A third application, and one which is quite relevant to this talk, of distributed key generation algorithms is for producing randomness beacons. And we've had a fair amount on these today already. A randomness beacon is strictly stronger than just a good source of randomness. The idea of a randomness beacon is that at time X, if enough people collude, then we can produce some randomness which could not be predicted at the previous time period. So this would not apply, to example, for hash functions, because if you have a hash function, sure, in the random oracle model, you can say it's a good source of randomness, but if you know the seed, then you know the randomness. And if you don't know the seed, then you have the problem of, well, how do I generate the seed in order to compute the randomness? And that becomes a randomness beacon problem. One way to build a randomness beacon, which was put forward by Definity, I think, originally, that is now used more by DRAND, is to first run a DKG. Then with your DKG, which produces a public key, you can compute, using your shared out secret key, unique threshold signatures on predetermined messages. And if T out of N people sign, then you can compute that signature. But if less than that sign, then you cannot compute that signature. And it doesn't matter who computes that signature. This is different from multi-signatures in this respect. Anyone can compute it and you'll get the same result. And at the end, because your unique signature probably isn't random enough, you just hash the output to then argue in the random oracle model, this is random. The notion is highly related to that of secret sharing. In fact, I don't know of any DKG that doesn't use secret sharing as sort of the base technical layer. A secret sharing scheme allows a single trusted dealer to generate a public key and then share out the secret. Might not be a public key, but for this talk, assume it is. Whereas a distributed key generation algorithm, you don't have that single point of trust. You say lots of different parties have to take part in the secret sharing scheme in order to compute the public key. I'd also say that most DKGs are inspired by some form of secret sharing scheme. Often it's the Feldman VSS, which is related to Shamir's secret sharing scheme, as is ours, I should add. But the secret sharing scheme which we took inspiration was one called Scrape by Cascugo and David. And this is basically one which they have two variants in the paper. One works for any discrete log group and the other works for pairing groups. We're looking at the one with respect to pairing groups. So I was saying that one of the big motivations of this work is the fact that it has no complaints rounds. And I'm now going to briefly describe what I mean by that. So in a DKG with a complaints round, how you would typically start is you would have some number of parties. I'm saying 3 parties here because it's easier than describing n parties, but some number of parties. And each party initially is going to generate some share of the public key, which they want to contribute to the full public key, and some share of the secret key. They then will broadcast their share of the public key such that everybody can see it and everybody knows what they want to contribute to the final result. But for sharing the secret key, obviously they can't broadcast this. What they do is they privately send out shares of the secret keys to all other parties. So you've got your first party here, they're sending out, they're having SK1, they're then splitting it into SK12 and SK13 next to the yellow arrows and sending one to P2 and one to P3. Then if P2 and P3 were to collaborate using those two values, they could recompute SK1, but if they didn't collaborate, they could not do this. And likewise, we have the same thing going on with P2 and P3. These are supposed to represent parties. The problem here is that you might have a situation where one party goes offline, or they might be malicious. And in the situation where they go offline, P2 is not going to receive anything from P1. They cannot prove that they haven't received anything from P1 because proving that you have not received a value is much more difficult than proving that you have received a value. So what they have to do instead is they have to broadcast a complaint. If they don't complain for whatever reason, then you can have a situation where any security claims that are proven secure for the scheme will not hold. So I've given a fairly sort of simplified overview here of what's going on. There are then more steps where maybe P2 lied, maybe they said that they didn't receive a message when they did, and then P1 has to say, actually, no, I did send you a message. Here's the message I was supposed to send you. And there's a few more steps in the process, but that's the overall idea. And if you're thinking this sounds complicated, you would be correct. It is quite complicated. And that means that it's quite difficult to implement correctly. There's a very large attack surface. There's lots of places where things can go wrong, especially if you then start to consider consensus layers. There's also a very long delay between rounds because parties have to be given enough time to complain. So if you have a setting where P2 doesn't receive anything, but maybe they've got fairly unstable internet connection and it takes them a long time to say, I didn't receive anything, then that complaint possibly won't get heard. So you need to make sure that it does. And likewise, if you had the situation where P2 does go offline, even momentarily here, then they might not receive their secret key share. And this would essentially mean that their participation later is going to be very difficult because they didn't receive their secret key share, they didn't get a chance to complain, they therefore don't have a single piece of their secret key, therefore they can't construct the secret key share that they need to sign, therefore that party is from that point on useless. So as I said earlier, our DKG does not have this property. We do not have complaints around. Instead, what we do is, as before, every party generates a contribution to the public and secret keys, and every party is going to broadcast their contribution to the public key. But for sharing the secret key, what they're instead going to do is they're going to send encryptions of these secret keys. I use the term encryption quite loosely here. It's not CPA secure, but it is hiding enough when you evaluate it with the full scheme. So because we are sending all of the data which could possibly be required to check that everyone is behaving honestly here, we are also able to attach proofs, proofs that we are behaving honestly. And this means that what you can do is you can take the information, you can take the proofs, and you can check that it's all okay. Even if you had nothing to do with the DKG, you're just a bystanding party. Because basically, if P1 were to produce a bad public key share as well, but let's say bad encryptions of the secret key shares, then that proof won't verify and everyone will be able to check that. So the idea of encrypting every message, as you might guess, when you have n parties, that means that you're going to have n encryptions per party. These are not going to be compressing their encryptions, they can't be. So you're going to end up with very large messages, n squared in total. So the reason why I would say we get away with this is because even though our initial messages, which everyone is sending out, are very large, we can aggregate them. So the result of that is that you're going to end up with the same large sized message at the end after you've combined everything as you would at the start when you have n lots of n sized n messages. So you just have one sized n message at the end to verify. And yeah, it's not like these aggregated messages grow as you add more participants. I mean, they do in the sense that you have like just a constant size signature per contribution, but certainly anything to do with the encryptions does not grow. So the message will be the same size no matter how many times you aggregate. Often when we talk about aggregating signatures, you'd have a situation where you could have two things you might do. Either you might have one central aggregator, which takes all of the signatures together, computes an aggregated signature, releases that, that's your signature. Or you might have the situation where one person takes a signature, aggregates it, and then another person takes a load of aggregated signatures and aggregates those. This is, for example, something that you can do with BLS. And the latter is quite powerful because what it means is that you can parallelize all the computation of the aggregation. You don't need to have sort of one very heavy computation. You can do it in little pieces. So our scheme is the latter. We can aggregate aggregated messages, we can aggregate aggregated messages, and we can do so in pretty much any order. And one further thing we can do is we can aggregate together two transcripts which have the same contributions from maybe 2 out of 5 players. So in the diagram I've presented here, you will, for example, see that in the pink row, you've got party 4 has supposedly got the shares from 3, 4, and 5, so 3 itself and 5. And likewise, party 1 has got shares from 1 and 4. When we now go on to the white blocks and aggregate those up, you'll see that both party 1 and party 4 have the aggregated value from party 4. This does not mean that we cannot aggregate that value. We still can. We can still take 1 and 4, and we can still take 3, 4, and 5, even though we've lost quite a lot of the information when aggregating, and aggregate those together at the end to get 1, 3, 4, and 5. So this means that we can very easily implement a gossip protocol in order to aggregate up our very large messages. And these rounds are quite, even though you have quite a lot of these rounds, they're quite efficient. It's not as if we're going to need to have a huge broadcast round between every aggregation process because you're only talking to a logarithmic number of players per round. However, we do need a broadcast at the end just to terminate. But the broadcast at the end will be just for a single message. It would not be for every single party having to do that. So if you had to ask me what is the downsides of this scheme, where are the places where we're perhaps not as competitive with the state of the art, it would be that the secrets we're producing are group elements rather than field elements. And what this means is it means that we cannot be applied to certain schemes. Certainly we cannot be applied to BLS signatures or algorithm encryptions. In fact, sort of, there are schemes which we are applicable to, but they have the specific property that the secret key is a group element. This is not a problem for the randomness beacon application, the reason being that we can build a verifiable unpredictable function which has a secret key as a group element. So remember the description I was giving before about how you might generate a random beacon, first using a DKG, then a unique threshold signature, then hash the outcome. And the main property that we needed of the unique threshold signature is that for each message, there is only one signature that verifies. Usually you would use BLS for this. We can't use BLS because our secrets are group elements, not field elements. But we call it a verifiable unpredictable function, but this does provide the same functionality really as a unique signature in this scheme. What it means is that there is a component which is unique, which you cannot predict if you don't have enough parties, but you can actually compute if you do have enough parties, and you can check that this is correct. The VRF we come up with, it's not quite as fast as BLS. It would be amazing if it was, but BLS is just a single group element, and that's very hard to beat. But it's actually not far off. We have two group elements, and verification is a bit confusing actually. It's we have the verification part, which consists of 3 pairings, and we also have a function we call derive, which is what you use to derive the unique component. And that derive function is also 3 pairings, and these must be computed separately. So you could still find yourself in a situation where this doesn't suffice and you really do want to use BLS or Algamal, or maybe some other scheme that I haven't thought of. You might be thinking, what do I do in this situation? And the answer would be that you're still going to need to use previous state of the art, which does have complaints rounds. They are doable. There's been lots of talks today about precisely how you might achieve them. It's just harder to achieve than if you don't have to do this. And we are able to prove security without rewinding, although to be fair, only in the case where you have half of parties honest, of the Pedersen DKG for these applications. Not for all applications, certainly not for Schnorr, I shall do that. But for the BLS signatures, we can do this, and for Algamal encryption, we can do this. If you are trying to generate a DKG in order to implement a Schnorr signature, be very, very careful. There are attacks in this area which are very unintuitive, and they basically take advantage of the fact that forking lemmas are confusing and previous security proofs were wrong because they hadn't properly thought out these forking lemmas. I think since then there have been some works which have tried to tackle Schnorr, and I haven't been able to verify them yet, but yeah, basically, unless you know what you're doing, be careful. So to wrap up, we have constructed a new DKG. It's publicly verifiable, aggregatable, and does not have complaints rounds. We can use gossip communication to reduce communication. We are able to build random beacons, and our proving techniques are highly applicable to other schemes. Thank you.
Thanks a lot, Mary. Are there any questions?
So my main question about this paper. So at the end, everyone's, many people might have aggregate keys, which will be a good, contain basically everyone's secret, and they just need to share them out. And so how does the sort of consensus on which aggregatable thing, which aggregated thing we use at the end work? Is there any easy way of doing that?
If I had to say easy, it depends what synchrony, what level of synchrony you have in your system. If you have a perfectly synchronous system, which we're assuming when we describe the paper, you can broadcast at the end. What we do is we say that you broadcast at the end. There is a probability of you being allowed to broadcast officially. such that we expect that there should be a maximum number of a logarithmic number of broadcasts at the end of that, and we just take the one with, I don't know, some desired property, maybe the highest bit count. If you're talking asynchrony, it's much more complicated.
So the main problem here is that these things aren't that small, right? They're order of n.
Yes, they are order of n, but again, you should not be broadcasting lots of them. You should only be broadcasting one of them. Well, a logarithmic number of them.
Hi, can I ask, sorry, can I ask a question? So I was wondering what are the properties you need from the PVSS? Because instead of using Scrape, I was wondering if one can use this new one that we had in ASACRIP 2020, Albatross, where we use, basically we prove the correctness of the sharing by using some Sigma protocol. So in general, what are the properties you need from the PVSS to run this aggregation?
Sigma protocol, I don't immediately know, but I would guess that if you're using a Sigma protocol, you probably can't use that one because basically they're not algebraic. You have a hash in the middle of your proof, which means that you're not going to be, even though you're going to be able to aggregate up your messages, maybe you're not going to be able to aggregate the proofs. Okay, so you won't get public verifiability, and you're talking about gossiping encryptions. Public verifiability is actually really important.
Yeah, so I suppose that you lose the linearity. I mean, I guess that's what you need, right? So to be able to have some linear properties. Okay, thanks.
So there is one thing I wanted to ask regarding the rewinding thing. So it depends upon what adversary assumption you make. So typically in the older, some of the earlier work, the rewinding was required against the adaptive security. So do we assume here adversary to be adversary as the static, or do we assume that to be adaptive?
I was very much assuming that the adversary was static. It's entirely possible that the techniques that we come up with here, because they're a lot more algebraic than your average ones, they might be helpful for proving adaptive security, but I've not looked into that at all.
Okay, so there is Rand Kennedy's paper from 99, that just a reference. Okay, and actually starting, so indeed, if I do not, I'm fine adding a complexity a bit more. It seems like we can go from the group element to the scalar ZQ, right? Okay. For the, in your case, one of the key challenge why we can't use in some of the schemes is that the output is a group element and not a scalar. But that's happening. That could change if one is willing to give up on the complexity, the communication complexity a little. Right or wrong?
I wouldn't immediately know how, actually. So the basic, if I had to give like a reason why I think this is the case, it's because we have very good homomorphic schemes for encrypting group elements. We do, I think if you use lattices, there are some homomorphic schemes for encrypting field elements. However, we don't know of any non-interactive, non-random oracle lattice zero knowledge proofs. So if you wanted to prove that your encryption was correct, that would be very difficult.
Yeah, I think there is one based on class group assumption, right? But that could be, there could be challenges with the efficiency
there. Yeah, I could picture that class groups might work. Yeah. I don't know though.
So Aline put out the exact citation for the paper. Did Jeff had a question, or is that just a comment, Fatima?
I think so. There was a comment by someone. We can also resolve this problem by posting on a blockchain, smiley. And then Jeff added some replies to that, saying that this would be too much traffic if you have a lot of validators. And then here he gives some number on some complexity notations. Mary, do you want to make maybe a comment about that?
No, it would depend how many validators you have, probably. If you only had a few validators, you could certainly do it on a blockchain. If you had lots of validators, it would get too heavy.
So one question related to that I have is that, so when you, in your practice setting, how you envision a broadcast channel then? Implementing a broadcast channel?
We had not. We merely assumed that there was one and it was synchronous.
Okay.
Sweeping a lot of the details under the rugs. It was not the focus of this work, really. Not that it's not important. It definitely would be if you were planning to implement it.
Okay, if there are no other questions, thank you again, Mary, for the interesting talk. And let's switch to the next speaker, and I will introduce him.